Hi there, I'm Andrew and I'm going to talk about Haskell and mathematics, and I'm going to do it in a bit unusual direction because we as a community of functional developers, we like to go other way around. We prefer take some fancy mathematical idea like can extensions and use it for our building system in Haskell. I'm going to talk about how to use Haskell in your mathematical research, in your science, basically. And bad news are that we are in crisis. Like scientific studies nowadays are so difficult to replicate that almost no one does it. American magazine Nature conducted a poll of like 1,500 scientists, asking them about reproducibility in their field. And it appeared that 70% of them tried to reproduce some other peer-reviewed, published experiment and failed. What is even more interesting is that half of them failed to reproduce their own published and peer-reviewed paper. And of course, this problem is mostly specific for like social sciences, for psychology, for medicine, and probably it's not surprising because it's very difficult to reproduce experiments in these fields, and it's difficult to interpret your results. You cannot use a free model, unfortunately. But are computer sciences and mathematics free of this plague of irreproducibility? And there is a very interesting paper 5 years ago by Kohlberg and company, University of Arizona. And they took 400 papers from recent ACM proceedings and conferences, and they tried to reproduce results. This was computer science. They selected papers which they potentially were able to reproduce. I mean, there were no like no weird exotic architectures. It was all like Intel CPUs or whatever. It was all like languages which they potentially were able to obtain some compilers. And the criterion of reproducibility was actually very weak. They deemed that the paper is reproducible if they can compile. Results are frustrating. Like, only for a third of papers they were able to compile source code without any issues. And like for a half, this is cumulative numbers. So about for half of papers, they were able to obtain source code and compile it with some effort, or at least authors of this paper coerced them to say that this can be built. The main reason, they were not able to obtain source code. And they list in their paper hilarious answers which they got from scientists working in computer science. I mean, I believe almost everyone can predict. So these answers are, oh, I'm sorry. Yes, we published a paper. Yes, it's peer-reviewed. Yes, it's cool. But you know, my code requires some polishing. I'll send you later. Never. Or, oh, you know, we had some students. We had some students to write some pieces of our software, and you know, these students have already graduated, left. We cannot send you any source code, and we don't even know how to build this system on our own infrastructure. But this is computer science, okay. And I remind you that reproducibility is just ability to build in this poll. What about mathematics? In mathematics, there is no like software, no architecture. You cannot hide your source code, presumably. There is your paper, you should read it, and you should be able to understand each line one by one. There is a famous ABC conjecture. The statement of it is very short. It basically says that if you have numbers ABC, and a plus b is c, then the divisors of the product of a, b, and c are somewhat limited by the value of c. I wouldn't dive deep into concrete meaning of the product of prime factors or whatever, but the main thing is that it's a simple conjecture. You can try it, you can have some numbers, a, b, and c. You can check that, yes, this product of distinct prime factors of a, b, c is somewhat limited, and whatever. And this is a part for which I love number theory, because in number theory, you have absolutely innocent problems which can be fit in 3 lines, and you can never prove them. It was the story with last Fermat theorem, which was unproved for like 300 years, and finally was done in 90th. But for ABC conjecture, the situation is even worse, because like 8 years ago, Japanese mathematician Mochizuki outlined the proof. His proof of this ABC conjecture took 500 pages in 4 separate papers. And mathematical community started to look into it, trying to read it and understand. And it's actually hilarious because like each time when some old famous conjecture in mathematics is to be proved, or at least to be claimed to be proved, like some people says, yeah, I understand everything here. It's all cool. I agree with this author, and it's true, it's cool, we proved it. And some other people are more cautious, and some people say, well, I don't understand his proof. Unfortunately, they do not say it loud, because, well, mate, are you stupid? And so, in this case, the proof was so dense that mathematicians in Oxford University conducted several workshops in 2 years trying to get a grasp of the ideas of Mochizuki. They basically failed. And 2 years later, another Japanese scientist published 300 pages of explanations, additional explanations to this Mochizuki proof, trying to make it crystal clear to the community. And next year, Scholze and Stix, well, they believe that they have found an issue. They believe that they found a bug, basically, in this proof. And more or less wide community agrees with them. Well, Mochizuki says that they don't understand that his proof is valid, and they just oversimplified his theory. We don't know actually who is right in this situation up to date. This is all very much frustrating. And I don't think that we can use like proof assistants in the nearest future, maybe in nearest at least 20 years, because these proofs are too dense for proof assistants, and no one in research, in actual like number theory community, almost no one is interested to spend all their career just to rewrite all textbook proofs onto some Agda or whatever. Everyone is in research community is interested to prove more dense theorems which no one could ever understand. It's not like there is no light in the science nowadays. And here is a quote of John Milner. John Milner is a famous topologist. So he says that if I can give an abstract proof of something, I'm happy. But if I can get a concrete computational proof which actually shows here is your object, here is your number, I'm much more happier. And he says that he is addicted to computers. I remind you, this has been written not 10 years ago and not 20 years ago. It was well in the 80s, I believe. It's a bit of a personal story for me because I got my PhD in number theory, and my PhD is very much abstract. It's all like proof of existence of something which I was never able to construct. I have only proved that it exists, but it was impossible to actually construct this thing. It was a source of tension between me and scientific advisor, because my scientific advisor despised everyone who is working with real numbers, with concrete digits. Everyone who was able to multiply two single-digit numbers in his mind is insane, I believe. No working mathematician should retain this skill. And I always loved to work with numbers, just grasp it, a small number. And the usual argument from pure mathematics here is that, come on guys, okay, you made some experiments. You tested your conjecture, your hypothesis on some billion of numbers. But it doesn't prove anything, right? Because our conjecture, our hypothesis, was that it holds for all numbers, no matter how big they are. So you're useless, guys, with these computers. Stop using them. Get back to abstract nonsense. And they're kind of right. It doesn't prove anything. No experiment in mathematics can prove that you're right, that your conjecture, which states something about all numbers, is right. This is another quote from Jonathan Borane, who is one of the leading mathematicians in computational number theory these days. And he says that basically this computational and experimental approach to pure math, it's intended to provide an insight. You basically can have this insight in your mind just without any computers. But if you have a computer and you can test your conjecture with more numbers, on more numbers than one, it's good. And maybe you can look closer, and maybe you can use some online databases of sequences, and maybe this sequence which you're learning about is something very well known. I very much agree with Professor Borane on this account. And again, back to my personal story, I was doing my PhD, and there were some tools for experimental mathematics and number theory. Very nice, hundreds of years of work there. But this library has two flavors. First one is C library, with all bad things associated with C libraries. It has short function names. Each function name had 20 or 30 variants with different suffixes, because some functions, you have one suffix for ints, another suffix for int32, another one for doubles, another one for complex numbers, and so whatever. And it has some very difficult memory model, it has its own stack, and it was horrible to work with. But it was fast. And another one was a wrapper around this C library, which was a Python-like language, very nice language, but purely interpreting. And it had no types, and it was very easy to make a mistake. I got so frustrated that I decided to learn Haskell. I dropped out of academic community. I found myself 5 years later somewhere in banking. Still don't quite understand how it happened to me. Maybe if I'll write more Haskell, I'll get back. I don't know yet. But basically, I started to work on making number theory well-typed, in my opinion and in my humble amount of time and efforts. And what I'm going to talk about today is actually how a working mathematician can use Haskell to develop mathematical libraries intended for mathematical research, so for experimental math, basically. I'll highlight some features of Haskell. They are probably well known to seasoned Haskellers, but they appear to be less known in mathematical community, and probably it's not always straightforward that these particular features are crucial for mathematics and efficient research. So I believe it's more or less common knowledge of a Boolean blindness. Like you have an API of your system, and in your API you have some functions which accepts Booleans. And you basically used Booleans because you needed some type with two values. So you just arbitrarily allocated that one value will correspond to true and another value will correspond to false. And no one actually knows without some documentation to your library which one is what. For example, here is a filter function. And filter function takes some predicate, it takes a list, and returns a list. But judging from only this type signature, I don't know what true value of the predicate means. Should I retain value in my list, or should I discard it, actually? It would be much better to use a domain-specific type. Like, yes, it sounds like we are multiplying things like this type action. It has two values, and it's very tempting to use Boolean instead. But come on, if we use like keep and discard, there is no more ambiguity what it means to keep or to discard. And in case of filter function, it's kind of maybe, okay, we have some conventions, we have some maybe general ideas that, yeah, probably our predicate should return true if we want to retain an element in the list. But when you have more than one Boolean in your function argument, it's worse. And Boolean blindness is so-so, because Boolean, anyway, holds only two values. What is worse is int blindness. If you have a function which accepts ints, like, for example, this function substring. So substring takes two ints, it takes some input string, and we assume that it returns a substring of the input. But what actually the second int argument stands for? Is it an offset in the string, like an absolute one? Or is it a count of symbols which has to be taken after the start position? In JavaScript, you even have two functions. You have function substr with the first semantics, where two int inputs are positions, and you have substring function which accepts offset and count. And usually you don't have much way to go around here. But in Haskell, we can just have this lightweight new type wrappers around ints to basically name them. Basically say that this one is offset, and we will always use it as an offset. And this one is a count, and we will use it as a count. And now our type signature of substring looks more easily to understand what's going on. Usually people from Python community and, funny enough, people from a camel community, they say, okay, you just lack named arguments in your Haskell. Why wouldn't you use them? But it seems to me that named arguments wouldn't help, actually, because I would also like to prohibit some invalid operations on my ints. Like, if I have two counts, it's okay to add them. and I'll get a count again. Like if I have something of length 3 and something of length 5, okay, probably in total I need something of length 8. And if I have an offset and some count, it's also okay to add them up, but in this case I should probably get an offset, a new offset in my string. It makes much less sense to prepend offset to a count, probably, and it makes no sense to add up two offsets. Like if you have two offsets in your memory and you added them up, you're in trouble. It doesn't, you're somewhere out of your memory. And if you're using just ints, you have a huge chance to hit this problem. And in mathematical libraries, it's very ubiquitous. Like you have functions which accepts like maybe 6 or 7 ints, and they do something interesting with all those ints. But if you are looking purely on type signature, you have no clue. This is a real example. Like this function takes 4 integer arguments, like 2 of them are signed and 2 of them are unsigned. But since all of them can be instantiated as literals, it doesn't matter much. So you have 4 integer arguments, which means that there are 24 options to swap them around. And you never guess which version is correct. It's very easy to make an error when you're writing some code. You just swap some arguments, and you will never know why you're getting wrong results. And in some numeric applications, you also have like double blindness, when all your inputs are doubles, and you have no idea which is what. So this is why nominal typing is when you distinguish types by their names, not by their structures. There is structural typing and nominal one. This is why nominal typing provided by Haskell is a huge win for such kind of libraries when you have several inputs of the same structure. This is point number 1. But now, when we when we use some new types, we probably need a separate function for each new type. We have more types around, and probably we need more function to cope with all of them. This is actually a screenshot from a user guide for LePack. LePack is a well-known package for linear algebra, and it's horrible. Like this is a table of function names. All these functions do precisely the same job. They work to solve linear equations. But depending on the form of your matrix, depending on your precision, depending on what kind of driver you're looking for, you have all these names. It's twice longer, doesn't fit slides, unfortunately. And all names are 6 letters, because who cares for readable names, right? So what we have to tackle this combinatorial blow-up of functions, like we had one function to work on all ints, for example. Now we have ints, we have counts, we have offsets, and something else. What can help us still to retain a uniform, neat, concise API? Yep. And Haskell is great for polymorphism. In Haskell, you can have parametric polymorphism when your function does not change depending on the nature of your inputs, which was exemplified by natural transformations in the previous talk. But also you have a very flexible ad hoc polymorphism, which basically you can define some interfaces and you define types which are conforming with these interfaces. And this type classes machinery in Haskell, it's also useful for other application in mathematics. Like just a short introduction to abstract algebra. Like you already heard about monoids, I believe, in the previous talk. But basically, if you have a set and you have an associative operation in this set, then this set and operation is called a semigroup. And if there is a neutral element, then it's called monoid. And if this operation is invertible, then this structure is called a group. And if this operation is also commutative, then this structure is called an abelian group. You shouldn't care about these names. The basic idea is that you have this like filter, like you have structures, and then mathematicians, they begin to filter these structures. Okay, they say, this subset of structures are semigroups. This subset of semigroups is monoids. This subset of monoids is groups. This subset of groups is abelian groups. And for example, if you have two sufficiently good, like invertible, associative, commutative operations, then your structure, which is equipped with two different operations, can be called a ring, a semi-ring, a rig, or RNG, or many other options. You see, like, we have rings, and we have something which is almost rings. So semi-rings, rings without n, rings without I, rings without something else. And there are like a dozen more structures, all the way from rings to fields. And people who know a lot of abstract algebra can't possibly even list them, but we don't care at the moment. The main idea is that you have some hierarchy of structures in mathematics. And this hierarchy is not very nice from object-oriented point of view because there are a lot of diamonds there. But in Haskell, you can use type classes. And growing through its history, Haskell developed a very flexible system of type classes, which can cope well with all your diamonds and whatever. This is a usual cell point here. That in Haskell you have type classes. You can use these type classes to model all your fine algebraic structures. The catch is that numeric classes in Haskell base package are very unfit. They are lawless. They have very weird dependencies. For example, in normal Haskell library, we say that some structure is integral, which means that you basically have division if it's enumeratable, which is very weird from algebraic perspective. And of course, in Haskell community is a solution. It's an algebra package developed by the same person who developed all those scan extensions and monads and categories by Ed Kmet, and it contains like 100 numeric classes carefully, very painfully reflecting all algebraic structures and their gradual growth. And of course, it's unusable. So I believe that we may find some good ground for a better numeric type classes in Haskell, which is because now we have some practical applications, like through some years, and I believe that this problem can be solved well. Linear algebra. We know that the determinant is defined only for square matrices. If you got a rectangular matrix, you cannot compute its determinant. And we know that matrix multiplication is defined only if these matrices are compatible in dimensions. So that means that if you want to have a well-behaved API, your determinant function that it should take a matrix and it cannot return just double because maybe your matrix was not square one. It should return maybe double. Maybe I return you your double, or maybe I say nothing. It was not a square. And your multiplication is also the same. It takes two matrices, and it returns maybe matrix or maybe nothing, if your matrices were incompatible. And the Haskell solution for this problem is that, you need to refine your types even more. You need to put numbers, like these normal numbers, you need to put them on type level, from term level to type level. For example, you can annotate your type of matrix with two integer numbers. So one will stay for width and another one for height. And in this case, you can have your nice total functions like determinant will take matrix which has two dimensions and n and n. And your compiler, your Haskell compiler, will check that they match. And the same for your multiplication. You have two matrices, and the width of the first one matches the height of the second one, and only in this case you'll get your result. And this is a total function, and it greatly helps you to clear mistakes in your some linear algebra transformations. The same idea, putting putting natural numbers on type level. It works for modular arithmetic. Like in modular arithmetic, which is ubiquitous in cryptography, you do all your computations modulo some big prime number usually. So your values, they hold value and modulo. And for example, your addition, it will take two values. It will check whether they have the same modulo. And if they do, then it will add values, reduce by modulo, and return. So for example, what happens if I have two values, both by modulo 7? First holds value 4, and another one holds 5. What is the result of this addition? Someone can say. Okay, yes, it's 2. And the solution is that, yet again, we can parameterize our types by type level numbers. So instead of keeping your modulo on term level, you should promote it to type level. And once you've done it, well, you have your addition and it's total. It has no more reason to return nothing when your moduli are incompatible, because you proved it on type level and your compiler checked your proof. This is again a huge source of errors, and I was beaten more than once by adding values computed by different modulo in my number theory work. And even more deeper thing is that sometimes you need so-called singleton types. For example, we call an integer r a square root of n modulo m if r squared equals to n reduced by modulo m. So for example, square root of 4 modulo 5 is, I believe, 3. Because if you take a square of 3, it's 9, and you reduce it by modulo 5, you get 4. The problem is that the algorithm, the efficient algorithm of computing square roots, it requires you to know factorization of your modulo. And as we know from cryptography, factorization is a very expensive operation. Like finding all prime factors of your number is expensive because they may be very huge and you have no efficient algorithm to do it. So if we have done it once, like we have some function factorized and we spend a lot of time factorizing our huge number 60, we would like, from this point on, we would like to be able to Oh, by the way, yeah. The type of this function is very bad. Like, this is an example of int blindness. Like, this function takes int, factorize, and returns a list of pairs of ints, which ints mean what? We would be much better in Haskell, yeah, if we use our nominal typing and we declare actually different types for primes and for powers. And in this case, factorize will return us a nice result. We will be able to understand from the pure type signature what's going on and which value is prime, which value is power, and probably guess what this factorization function is doing. And so we would like probably to, instead of factorizing modulo m each time, we would probably pass its factorization to modular square root as an argument. But this is a recipe for disaster because now there is no link between modulo m and its factorization. We can easily mess up and use factorization of completely different modulo here. And what will save us? It's singleton types. Singleton types are a special technique in Haskell which basically gives you a strange thing. It's a type parameterized by some other value, usually, by some term level natural number in our case. And this type is inhabited only with one value only, with one possible value. For example, we can describe a singleton type for factorizations as factors, which will hold modulo m on type level, and which will hold factorization of this modulo m on term level. And once we have this one-to-one correspondence ensured by smart constructors or whatever means we choose to implement our singleton type, we can actually pass this singleton to modular square root, and type checker will check that we are using a factorization of right m here. We also can leverage Haskell ability for laziness to represent mathematical structures easily. I believe, so for example, in mathematics, we have this set construction notation, which is used to describe how you construct sets from their components. Like you say, like x is 1 or 3, between 1 and 3, y is between x and 4, and sum of x and y is below 5. List me all pairs of this type. This construction can be translated into Haskell one-to-one, basically without any changes. But mathematics also operates with infinite lists. For example, I can describe a list of number of even numbers which are divisible by 3, and it's an infinite construction. And in eager computation model, you cannot represent it nicely. But in Haskell again, it's no trouble. You just write the same expression as you have written in mathematical notation. More complex sets, more complex infinite sets are also doable. You can probably do something like this. There is a catch that this Haskell expression wouldn't be as productive as we would like it to be. But there is also a nice library which will make it interleaving two infinite lists in one together. One more application of laziness is again factorization. As we discussed, factorization is a very expensive operation. So if we have this routine which returns a full factorization of your number, but there are many applications in which you do not need all factors. Probably you need only first factor of your number. And what would we do? Should we write some helper which will return specifically first factor and stop factorization after it found it. And what if we need 2 factors, 3 factors, something else? It will clutter our API very soon. So in Haskell, thanks to laziness, we are happy to compose. We can just use our full-fledged factorize, which will potentially factorize your number to the very end. But we will just take a head of this list, and thanks to laziness, all computations will stop after the first element. So this means that laziness in Haskell, it improves composability. Better composability means smaller API. Smaller API means that our libraries can be simpler, and we, mathematicians, will spend less efforts maintaining them, because maintaining libraries is a pain. Recurrent sequences, like this is a popular thing in number theory and combinatorics, and here are Fibonacci numbers, and here is naive solution of Fibonacci numbers, and everyone knows that this solution is bad. It behaves horrible in runtime, and there is a nice Haskell solution which uses a lazy list again, as a cache to basically bootstrap Fibonacci numbers from their first elements. But it looks like a cheating, because, come on, okay, we were very much lucky that we were able to construct this, we were very much lucky to construct such nice expression like this, like it's just so easy that we just need to take a list and the tail of this list and sum up them. What happens if we have some more horrible recurrent relation? Would we still be able to cover it in Haskell? This is, for example, a recurrent sequence of values of Riemann zeta function. And it's not even easy to grasp from the first approach what defines what. I highlighted in red values of zeta Riemann function on odd arguments. Can we express this function in a nice way in Haskell? And it appears that yes, that there is a regular generic approach to untying recurrent sequences in Haskell. And moreover, you can split computation itself and caching layer, and you can compose computations and caching layers all in pure semantics in any way you would like. We're almost done. So our last problem for today. Mathematical objects are pure, immutable, and lazy. And Haskell's solution for this problem is that Haskell is pure, immutable, and lazy. Haskell gives you more concise APIs for mathematical libraries. Haskell gives you laziness. Haskell gives you very much precise types. That's it.